I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on potential energy and escape velocity and how to derive expressions for both. So in this video, we're going to approach the outer space centripetal force from potential energy and derive an expression for escape velocity. So first, let's start with potential energy. So the equation for potential energy is negative g, we have the two masses, divided by r. Now, you may remember back when we started talking about energy, we had the textbook definition of gravitational potential energy, which is zero at an infinite distance, and it becomes increasingly negative as it approaches the Earth. So this is the equation that we would use to calculate. And if we look at the universal law of gravity, force times distance, we'd end up with the opposite of potential energy. So force is equal to the negative of potential energy. So that's where the negative value comes from. So when we talk about the potential energy of a system, the way we'd approach this problem here is we have three masses that are moved from an infinite distance away to the location that is shown here. So steps that we would use to solve this problem is the first step, we'd find the potential energy between each pair of masses. So we'd use the top 2m and the left m, the top 2m and the right m, and then the bottom 2 m's, and calculate the gravitational potential energy between each sets. And then we would just simply add the values together. So using UG, we have negative GMM divided by R, that would be the bottom pair. Negative G2M times M divided by R, that would be the left and the top one. And negative G2M times M divided by R, that would be the right and the top one. So then we can just take those coefficients out in front. We'd have negative 1 minus 2 times GMM divided by R, which would give us a total gravitational potential energy of negative 5 GMM divided by R. So this is how you would calculate the potential energy of a system when it states that the objects are moved from an infinite distance away to the location shown. Just use the negative g m times m divided by r. So now let's look at deriving escape velocity. So what is escape velocity? Well, escape velocity is how fast you need to move to escape the gravitational pull of the Earth. So we're going to start with conservation of energy. So we know that the change in kinetic plus the change in potential is going to equal 0, which means the change in kinetic is equal to the negative change in potential. Well, since we're talking about outer space, we're going to use the potential energy equation that we just learned. And since it's negative, it cancels out with the negative in the equation, so that makes it positive. And then we use kinetic energy 1/2 mv squared, where ms is the mass of the satellite, and v would be the escape velocity. So we cancel out the masses of the satellite, or whatever is trying to escape the gravitational pull, and then we multiply by 2, take the square root, and we get the equation that the escape velocity is equal to the square root of 2g times me divided by r. So we can see that the escape velocity is inversely related to the radius, which means the closer you are to the surface of the Earth, the faster you'd have to be moving to escape the Earth's gravity, which makes sense because the g value is greater as we get closer to the surface of the Earth, and it decreases as we move further away from the Earth. So the further you are away, the less speed you would need to escape the gravitational pull of the Earth. So this is potential energy and escape velocity. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, don't forget to click the like button down below and subscribe to my channel, Cavi Coaches, and follow me on Instagram and Twitter at Cavi Coaches.